So we're going to talk about recommender systems, and we're going to start with very simple algorithms in terms of recommender systems, and then we're going to go to the bilinear formulation for latent factor models in recommender system, and then we're going to go to a probably in this lecture, in the next lecture, we're going to talk about how modern recommender systems work, how are they going to be combined with deep learning to achieve better performance. So you can think of this lecture as the foundation of the next lecture of the more advanced recommender system, and more kind of closer to the theme of machine learning. So recommender system. A typical example of recommender system is, for example, if you have a customer X, and this customer X buys an iPhone, and then he buys an iPhone case, and then we're going to have a customer Y. The customer Y, maybe he does some search on iPhone, and when the recommender system sees that this custom does search on iPhone, and it's going to quickly recommend both iPhone, of course, and also some iPhone cases to customer Y according to the data from customer X. So this is a very, very simple idea of how recommender systems work. So the basic pipeline is that you have a customer or user here, and you have a large database of product or websites and blogs, basically all the things you want to sell. And then this customer or user will search for something, and after the customer searches something, the recommender system will recommend a list of products or websites to this customer. So sometimes the user doesn't even need to perform this first step of searching. The recommender system will also automatically recommend something to this user. So the search step is not really necessary sometimes. So there is a lot of examples where recommender system is very helpful. For example, Amazon can recommend to you the product, right? And Pandora can recommend music to you. YouTube recommend videos to you, and Netflix recommend movies and dramas for you. So this is very commonly used. You might think that in terms of the applications of machine learning, you might think that computer vision and natural language processing are the largest application, but in fact the most profitable, at least one of the most profitable applications of machine learning is actually recommender system, because recommender system helps you sell things, right? And it actually generates a lot of profits in the industry. So what are different types of recommender system? In the old days, the recommender system used to be very simple. For example, it can be editorial or hand curated. Basically, it just gives you a list of favorites from other people. So this is not even personalized recommendation, right? I can say it's just you log into the website, and the website just going to give you a list of favorites or a list of essential items. This is the oldest form of recommender system. And there's another form of non-personalized recommender system, which is just to provide a simple aggregate. For example, you can provide the top 10 something, for example, top 10 movies or top 10 products from Amazon, or top 10 movie from Netflix, or can provide you a list of the most popular videos or movies on the website, or recent uploads or recently released movies. So these are also simple aggregates. It recommends to you the list of items, and what should appear in the list depends simply on some statistical aggregation, right? So this is too simple recommender system. It's non-personalized. And in modern days, when we talk about recommender system, we usually refer to personalized recommender system, which is a system that can recommend to you things tailored to the individual's users. Right? For example, Amazon is going to recommend different things to different users, right? And Netflix as well. Right? So formally, we can actually define this problem of recommender system. Let's say that we have X as the set of customers or users, and S is as the set of items. Then we can basically define a utility function. The utility function takes a pair of user and item, and the utility function will return some rating. So this rating can be an integer or it can be a real number. So R is the set of all possible ratings. So this is a utility function. And what's important is R is actually a totally ordered set. So for example, it can be any number from 0 to 5, right? This is going to be a set, or it can be a real number between 0 and 1. Okay. So a more concrete example. So this is the utility function. The utility function shows, for example, you can take a pair of users and items. Imagine that we're in the movie recommender system. Then we're going to take a pair of user, Alice, and movie, Avatar. And this utility function is going to return to us some utility. So the larger the better, and assuming we're in the range of 0 to 1. Right? So this is 0 to 1. And the utility function gives you one value for each pair of user and item. So if you take Alice and Avatar, so Alice is a user, right? Avatar is a movie. The utility function is going to return 1. If you take Alice and Matrix, the utility function is going to return 0.2. Right? And imagine you have 4 users and 4 movies. It's going to give you a whole 4x4 matrix, right? Although some of the entries are actually unobserved, because ultimately you would like to, in the recommender system, you would like to predict the unobserved, we call this unobserved ratings, given the observed ratings. So this is recommender system. So given the observed data, you would like to kind of predict whether Alice likes this movie LTR, or whether Alice likes this movie Parents. Right? If you predict that Alice likes some of the movies, then you can recommend to Alice this movie, right? And then you can kind of boost your sales of movies, basically. Anyone has any question about the setting and goal of recommender system? I hope you're still, I think we're all experiencing firsthand what recommender systems are. So the key problem of recommender system, we have 3 key problems we're going to talk about at least in the first half of this lecture. The first key problem is to gather the known ratings for the matrix. So to gather the data such that you can train your model on. This is actually very important. So how to collect the data in the utility matrix. The second key problem is to predict the unknown ratings, right? Predict the unknown ratings from the known ratings. So this one, and there's a important property of the recommender system is that we're mainly interested in high unknown ratings. So basically, we're not interested in knowing what you don't like. We're more interested in knowing what you do like, because if we know what you do like, we can recommend something to you, right? And this is what make a recommender system profitable. It can boost the sales of products. Okay. And the third problem is how do you evaluate recommender system methods. So the recommender system is very different from traditional machine learning problem. For example, in regression, you only need to measure the distance between your prediction and the ground truth. I take the L2 loss, and this is usually how you measure it. or in classification problem, it's just compute the accuracy. But in recommender system, sometimes it's more tricky to evaluate one specific methods. So how do you measure success and performance of recommender methods? It's also a key problem in recommender system. And we're going to talk about these three problems one by one. Of course, the most complicated problem would be the second problem. Right? So for the first problem, gathering ratings, roughly speaking, there are two categories of methods in terms of gathering ratings from users. The first one is explicit feedback. So this is literally by definition, explicit feedback means that you are asking people to rate items, right? But these usually do not work quite well because people do not like to be bothered. Right? Imagine you ask every time someone buys some product, it's going to be very annoying. So over the times, another type of collecting data is becoming increasingly popular, which is implicit feedback. Implicit feedback learn the ratings from user directly from the user's actions. For example, if a user buys something, then that kind of implies that this user like some products, right? And or for example, if the user is watching a TV show or TV series, the user watch the whole episode or even the whole season, that means the user liked this season or like this TV series very much, right? Otherwise, you will not just watch the whole season, watch the whole episode. So this is kind of the implicit feedback you can get, right? And it's actually quite useful and quite informative. Right? So implicit feedback can give you positive ratings, but how about possible low ratings? For example, we can actually collect the data about the items or products that the user has viewed on the website but didn't buy, or some products that the user returned to the seller to get a refund. So these are the items that the user do not like, right? So implicit feedback, it can give you both positive and negative feedback as well. Okay. So this is the first part, gathering ratings. The second one, so this is not a content, the true content that we're going to discuss about. This is an overview. So predicting utilities, this is the second problem. So the key challenge here is that the utility matrix is actually very sparse. So imagine that in Amazon or in Netflix, you actually have millions of users, and you have, for example, thousands of products in Netflix, or you have like millions of items at Amazon. So usually this matrix will be very large, but it's also very sparse because only for each item, only a few users may have rated them. Right? So most people have not rated most items. So this is this sparsity problem is actually very key as you go into the details of recommender system methods. You're going to see this is kind of the key distinguisher between recommender systems and other machine learning problems. So because this matrix is usually sparse, we're usually gonna run into cold start problems. So we have item cold start problems. That means there is always going to be new items that have no ratings. So if you have new items that has no ratings, then it's actually very difficult for the system to recommend these items to some users, right? And another problem is new users. For new users that have no histories, then it's actually very difficult to recommend something to this user as well, because they know nothing about the user. Right? So basically, the recommender system methods tries to tackle these problems. So there were three types of approach that we're going to talk about. The first two types is content-based methods and collaborative filtering-based methods. And if we have time, we're going to go through the latent factor models, which is basically the closest, I think is the kind of the more machine learning part of the methods. And it's also why we call it bilinear model. And maybe in the next lecture, we're going to talk about something more advanced. So basically, how do we combine modern deep learning with this kind of latent factor models to even further improve performance of recommender system. Okay. So any questions so far? So far it has been relatively high level. So let's talk about the first type of methods, okay? Content-based recommender system. So what's content-based recommender system? The main idea is to recommend items to a user, recommends items to a user similar to previous items rated highly by the same user. Let's have an example. For example, in movie recommender system, after a user has rented or watched some movies, our recommender system can collect the information about the movies that has been watched by the user, right? What actors are in the movie, what directors is the movie from, and then the system can directly recommend movies with the same actors or director or genre to these users, right? So this is a typical example of content-based recommender system. And for example, recommending websites or blogs, news, this is very similar. The recommender system can always recommend other sites to the user with similar contents that the user has watched before. So this is very straightforward content-based recommender system. So more concretely, let's say that we have a user here. It's a very simple example. We have a user, and this user likes red circle and red triangle. So we're going to build profiles for each item that the user like. And specifically, we're going to have, let's say that we're going to have a 4-dimensional vector to describe an item. The first one, the first dimension is called is red, so whether this item is red. And the second would be whether this item is circle. Let me make it small, closer. Is circle. And the third one is whether it's triangle. And the last one is whether it's rectangle. Okay. Whether it's rectangle. Okay. And if you look at the two items that this user like, the first item is a red circle, right? So it's red and it's circle, but it's not triangle, and it's not rectangle. But the second one is it's red, but it's not circle, it's triangle, it's not rectangle. Okay. So this is how we build a item profile. Okay. So we build item profile for each item that the user like. This is the first step. And the second step is to build a user profile, because you have the item profile and you know the user likes this item. Therefore, we can build a user profile. There are multiple ways to build a user profile. Item 1, item 2. One way to do it is to take a OR operator, right? So as long as one of these two are active, so this user used to like something red, so we're going to assume that this user liked the color red. This user used to like something that's circle. Therefore, we're going to assume that the user likes circles and triangle. But we haven't seen this user like anything that is rectangle, so we're going to put it as negative. So this is one way of building the user profile. So after you build the user profile, this is the second step. You're going to search in your database. Right? You're going to search in the database what are the items that matches this user's profile. Essentially, you're going to search for items that are either red, circle, or triangle, right? And ultimately, you can kind of imagine that the system will recommend these first two items to the user, right? Because the first one is red, the second one is circle. It seems to be something that this user would like, right? It's going to recommend these two items to the user. So this is the brief overview of these 3 steps. Content-based recommender system. Any questions so far? Assume what? We know the what of the user? Yeah, you need to know the user history. So what the user liked. Yeah. We're going to talk about this later. So we're going to have a more concrete example. For example, if you're recommending movies, then the feature will be something like what's the genre of the movie, right? So each genre will be this genre thing will be, imagine you have a 20 genre, then you're going to have a 20-dimensional binary vector, right? And another key property of each movie would be director and actor. So for each actor, you are going to have a 1-dimensional binary entry dedicated to them. So basically, you're going to build a very long vector to profile each movie. And this is already a simpler case. But imagine you want to recommend text, and text, it has a very large vocabulary. So this is something that we're going to talk about too later in this lecture. Okay. Cool. Any more questions? Cool. So this is content-based, an overview of content-based. Okay. So let's talk a bit more on this in a more concrete and more complicated settings. So basically, for each item, we're gonna create an item profile, right? We're gonna create an item profile. Basically, you can see that profile is actually just a set of features or vector of features, right? And in terms, for example, movies, these features will, for example, would be the author, director of the movie, author of this, the script of the movie, title, actor, and director. Right? So these can all be part of the features for the movie. And if you're recommending text, then text is kind of more tricky one because text has a very large vocabulary. For example, 20,000 words in total. Then you might need a 20,000 dimensional vector to represent each text. And then you're going to quickly run into the curse of dimensionality because you need a lot of parameters to describe what user like and what user don't like. So the usual way to do this is to just select a small set of important words in the document to describe each document. And how do you do this? So this is usually referred to as TF-IDF. So it's term frequency and inverse document frequency. So this method it's not limited to. It's actually not limited to text, right? You can see that term frequency. The term can be a word in the document. it can also be some feature, right? It can also be some feature in the movies, right? And selecting important words in the document, it's kind of like selecting important features, right, to describe a movie. So it's actually not limited to text recommendation. So TF stands for term frequency. IDF stands for inverse document frequency. Right? And this document, right, again, this document can be general. It can be any item. It can be really textual document. It can also be some items, for example, movies. Okay? And in the next slides, we're going to talk about how to compute TF, IDF in detail. So we're going to talk about what's TF and what's IDF. Okay. So first of all, what's TF? TF is term frequency. So basically, we would like to use TF, IDF to recommend how important a specific word is, right? How important a feature is. And TF just compute the frequency, how often this word appear in the document. If a word appear very often in the document, that means this word is very important, right? For example, there is an article news on how Twitter lay off its employees, and in this article, Elon Musk appear many times, and that means Elon Musk, this word is actually very important, right, in this document. So this is what exactly is computed here. So TF IJ means the term frequency of a specific term, for example, a specific word in document J. Right? And to compute this, you just count how many times this term I or this word I appear in this document J. And since this is actually an unbounded number, because a word can appear many times, we need to normalize it. So we're going to normalize it. We're going to divide it by the maximum term frequency over all the words. This is the maximum term frequency, such that it's the range of TF would be between 0 and 1. Okay. So this is term frequency. It measures how often a term appear in one document. So we have two subscripts, I and J. Right. I indexes the terms, J indexes the document. Okay. This is term frequency. But how about if you consider a very annoying special case, for example, the word the, THE, and the word actually happens a lot in all the documents, right? It appears very frequently, but it contains little information. So how do you compensate for that? You don't want, if you purely base your feature on term frequency, then these words, we call it stop words. These stop words will kind of dominate your feature vector. So to compensate for this, we need another thing that's called inverse document frequency to measure the importance or how common a word appear in the set of all the documents. So IDF of a document of a word I can be computed as a log of n over ni. So n is the number of total documents, right? And ni is the number of documents that mention term I. So if every document has mentioned the word the, that means ni will be n, right? Will be capital N. Then this whole IDF will be 0. Right? Then if you multiply IDF with TF, the weight for this word the in the document J would be exactly 0, because IDF of the word the would be 0. Right? So this is why people use TF IDF, because they balance two things: balance term frequency and how unique a word is, basically how informative a word is. Right? And so back to our point, given a lot of documents, how do you build an item profile for these documents? Usually, for each document, you're going to compute the TF IDF for each document, right? For each document J, you're going to compute the TF IDF for different I, right? And imagine you have 2,000 words in the category. Then for each document, you're gonna this I will go from 1 to 2,000. That means for each document, you're gonna have a 2,000 dimensional vector of TF-IDF. And then we're gonna select only the entries with the highest TF-IDF. So we're gonna remove most of them and only keep just a fraction of them, right? And to get together with their scores. So this is how you build a item profile for documents, for text. Any questions so far? So you can kind of imagine that this is for text, but it can also be for movies, right? Because you have thousands of movies in the world, and therefore it can have tens of thousands of actors or directors in the world. And if you want to build a profile for a movie, that means you need to have a tens of thousands of dimensions of features in the profile of each movie. That's basically the same as the document profile, and therefore you will need to select the features that are most important. You can use TF-IDF, for example. Right? Okay, so you can kind of see that this is a recap of the content-based method. The content-based method, one of the key step here is to build a user profile. We talk about how to build an item profile, right? However complicated it is. And the second key step would be to build a user profile from the item profile. And this is only one special case, right? When you can aggregate the item profile in some way such that you can get your user profile, right? And in general, there can be multiple ways of aggregating the item profiles to get your user profile. You can have a weighted average of all the rated item profile. For example, you can have instead of doing this, you can say that this user profile is actually, you can just take the average of these two, take the average of these two, 0.5 and 0.5. Right? So you can also build it as some kind of average of the item profile. Right? And you can also kind of, if it's movie rating, right? You can build the item profile with the average of only the top rated items. You don't need to take into account all the items. You only need to take into account some top items. Right? For example, if this user rate this item as 5, so the range is 1 to 5 stars. So 5 is the best, and the user rated this item 1 as 5, and the user rated this item 2 as maybe 3.5. It's good, but it's not that good. Therefore, you can directly use this item 1, which is highly rated by the user, as your user profile instead of using them both. This is different way of computing the user profile. And in terms of step-free prediction or recommendation, this is another key question. After you build a profile for every user, and after you build a profile for every item, and what kind of items would you choose to recommend to a user? Right? So each user profile is a vector, right? And each item profile is also a vector. Therefore, we can compute the similarity for each pair of user and item, and we call it. We can use it as an estimate of the utility score. Right? Utility score, we can estimate it as a cosine similarity. We call this a cosine similarity because it basically computes the cosine of that angle between these two vectors. So concretely, we can compute it as the inner product of the user profile x and the item profile I divided by the L2 norm of this x and I. So this L2 norm basically, it represents what? It represents the length of this vector, right? I hope you still remember this L2 norm represents the length of the vector. Okay. So basically, larger number means you have a smaller angle, right? Because you have cosine. Larger number means you have a smaller angle, and that means you have larger similarity. Then after you compute the cosine similarity between each pair of users and items, and given one user, you're going to recommend to this user the item that has the largest similarity. Right? Basically, you can compute all the cosine similarity between all the items and this user, and then you can rank them, and you can recommend only the top 10 to the user or top 20 to the user. So this is recommender system. So basically the simplest kind of personalized recommender system, content-based recommender system. Any questions so far? Okay. So what are some advantages of content-based recommender system? One advantage is there's no need for data on other users, right? Because all you need to do is to build a item profile for each item and build a user profile for each user. So no matter how sparse the matrix is, as long as there is some ratings, right? You can as long as one user has at least rated one item, you can already build the user profile for this user, right? So it's less effective by the sparsity of the utility matrix. The second one is it's able to recommend to users with unique tastes, because you're building a user profile for each user will have a different user profile, right? So you can kind of cater you to your different tastes, however unique it is. The third one is it's able to recommend new or unpopular items, because the recommendation process itself does not look at how popular each item is, right? It just look at the attributes or the features of each item. Therefore, it's kind of basically fair to the popular and unpopular items. And the last one will be it's able to provide explanations, because these features themselves can serve as explanations, right? It can provide explanations of the recommended items by listing the content features that cause the recommendation. For example, we can say that we're recommending the movie Matrix to you because you seem to like sci-fi movies. We can see that sci-fi here is one dimension of the feature, right? You can use this feature to explain your recommender system. Okay. So this is advantage. How about disadvantages? So one disadvantage of content-based recommender system is that finding the appropriate feature is actually hard. For example, in text, if it's textual documents, then you can still use some kind of TF-IDF. But how about images? Right? Consider an image. How do you find the appropriate features? This is before deep learning. In deep learning, you can always extract some dense vector to represent images. But without deep learning, it's actually very difficult to do this. Right? And movies, music, if you don't have any metadata about the movie, imagine you were only given the video of the movie and you're not given the director, actor, and all the other information of the movie. How do you build a profile for each movie? It's also quite difficult because all you have is a unstructured video. The second disadvantage is it's actually rely on user history. If a user haven't even rated one item, then it's impossible to build a user profile for this user. Right? How to build a user profile without user history? It's always going to be a problem. The third one is over-specification. So basically, you never recommend. It's never going to recommend items outside of the user's content profile, right? Because you're going to choose items to recommend purely based on the user profile. Right? And people might have different interests, but if you recommend purely based on the user profile, you may only capture one specific part of its interest, right? And of course, the most important disadvantage that severely harms its performance accuracy is content-based method is unable to exploit the quality judgments of other users. So you can see that when you're building the profile, user profile, item profile, it actually does not care anything about what other users think, right? But these can be very important. And if you use this, it may dramatically improve your performance of the recommender system. So in the next part, we're going to talk about collaborative filtering, which can help the system to harness the quality judgments of other users. And by doing this, we're able to dramatically improve the recommender system accuracy. Okay. So before I move on, to make sure there's any questions on content-based approach, any question that needs to be clarified, or we can move on. Okay, so we're going to start the part for collaborative filtering. So what's collaborative filtering? The basic idea of collaborative filtering is that, for example, let's say that we have a user X, and we are trying to predict the user X's rating on some items, right? But how do you predict the user X's rating on some items? The first step we're going to do is we're going to find a set N of other users whose ratings are similar to X's ratings. So we're going to find someone who has a similar taste as user X. After finding this, so N kind of stands for neighbors, right? So that you have similar taste. So after doing this, you're going to estimate user X's ratings based on the ratings of other users in the neighborhood. Right? So you can see that this is actually very similar to our k-nearest neighbor method. Right? First step, you're going to find some neighbors, and then you're going to predict based on your neighbors' labels. Right? To give you a very, very simple example. Let's say that we have 4 users and 3 movies, right? 4 users, 3 movies, and we have a rating system that is from 1 star to 5 stars. So for the user X, we're going to have 3 movies, movie 1, movie 2, and movie 3. And for user X, the rating user X has for movie 1 is 4, and the rating he has for movie 2 is 5. And our goal is to predict user X's rating on movie 3. So this is our goal. And let's say that we have another user, user Y. The user Y's rating on movie 1 to 3 are 4, 5, and let me see, 5. Okay. And we have a user Z whose rating for these movies are 4, 5, 4. And then we have the last user rating his rating is 1, 2, 1, 2, 1. So what are you going to do? If you this user X is what we're trying to predict, we're trying to recommend for, right? And if you look at the two ratings this user provide for these two movies, and if you look at user Y and user Z, you're going to find that they're actually very similar, right? So Y and Z, they actually have a similar taste as user X. Therefore, we're going to put these two users in the neighborhood set. How about W? W seems to have the exactly opposite taste as user X, right? Because user X likes these two movies, but user W doesn't like these two movies, right? So only Y and Z would be put into this neighborhood set. And then how do you predict the rating user X has for movie 3? You just look at their neighbors. So their neighbors, one of the neighbors says, oh, it's a good movie, very good movie, 5-star movie, and another says it's a 4-star movie. Then you're going to take the average of them and predict that is 4.5. So this is a very simple example of collaborative filtering based on user neighborhood. Okay. Any questions so far? If a movie doesn't have any ratings, then you, for example, you have movie 1 and this movie 1 doesn't have any ratings, then you cannot use this movie as to compute the similarity between users. The only thing you can rely on is movie 2. Right? We're going to talk about this in more details because this is just a simple example, and there is a lot of tricky things you need to think of when you're computing the similarity between users. Cool. Any more questions? That was a good one. So we can kind of see why it's called collaborative filtering, because it's basically filtering movies using other users. Right? Collaborative means using other users' data. Filtering means that you're filtering movies, filtering items. Okay. So this is, like I said, computing the similarity between different users might be very, very tricky. What we have here is a very simple example that you know that right away user X, Y, Z, they're very similar. But in reality, things can be a lot more tricky. Let's look at this example. Let's say that you have 4 users, A, B, C, D, and you have seven movies, right? 7 movies, HP1, HP2, all the way to HP3, TW and SW1, SW2, SW3. So this is like Star Wars 1, Star Wars 2, Star Wars 3. Okay. So we have 7 movies. And if you look at the rating matrix, right, intuitively, if you look at user 1 and user 2, user 1 and user 2, they both like, so again, the rating system is from 1 star to 5 star. 5 stars say representing the best ratings. So if you look at user 1 and user 2, you can see that both of them like HP1 very much. And that means we're going to think that user 1 and user A and user B, they have very similar tastes. And then if you look at user A and user C, here they basically have the opposite ratings. Right? User A likes TW very much, but user C hated basically. But on the other hand, user A doesn't like SW1 very much, but user C like it very much. Right? So basically, they have the opposite taste. So intuitively, what we want is we want similarity between 1 and A and B to be much larger than the similarity of 1 and C. Right? But if we compute the Jaccard similarity between A and B and between A and C, this is what we get. So what's Jacquard similarity? Jacquard similarity is also referred to as IOU, intersection over union. It's a fraction. It's a fraction, and in the numerator 1, basically it's the number of movies that user A and user B both rated. Right? So if you look at the ratings from user A and B, they both rated HP1, right? They only both rated this movie. Therefore, we have a 1 here. And the denominator is the union. It's the union of the movies that user A and B rated. So if you look at user A and B ratings, you're going to see that there are 5 movies they have rated, right? HP1, 2, 3, TW, and SW1. So the denominator is 5. Therefore, the Jacquard similarity between A and B is 1 over 5. And similarly, we can compute the Jacquard similarity between A and C. And you can see that in terms of Jacquard similarity, A and C actually has a larger similarity than A and B. So this is because when you're computing Jacquard similarity, you actually ignore the actual ratings. Right? You only care about whether these users have watched the movie or not, but you do not care about the ratings. So how about we take into account the ratings this time, and like I said, compute the cosine distance between 2 movies. This is slightly better. If you compute the cosine similarity directly between A and B, you get a number of 0.38. Right? If you compute the cosine similarity between A and C, you're going to get 0.322. So it's slightly larger. So it's at least better than Jacquard similarity. But it seems that these 2 numbers are still very close, right? Why is this happening? It's happening because you can see that we have a lot of missing entries in this matrix. And when we're computing the cosine similarity, we treated these missing entries as 0, right? Then these zeros basically is equivalent to saying that this user does not like this movie. So these missing ratings, they are interpreted as negative. And because most of them are missing, that means most of them are treated as negative, then the cosine similarity will be misled into thinking that, okay, A and C, they both hated a lot of movies, therefore they're actually quite similar in terms of taste. So we don't want that. The way to circumvent this problem is to subtract the mean. So you can basically compute the mean rating for A. For example, the mean rating for A is the mean rating for A is 10 over 3, right? You just subtract everything subtract 10 over 3 from every ratings, and this is what you get. And similarly for B, you can see that the mean rating is 14 over 3. Then you can subtract, for example, 5. 5 minus 14 over 3 is going to be 1 over 3. Right? So you can do this for all the users. And then, whenever you have a missing entry, you can safely set it to 0, right? Because now 0, it doesn't mean negative. After you subtract the mean, 0 actually means neutral, right? Then you can like treat these missing entries as 0 safely, and then you can go ahead and compute your cosine similarity between each pair of users. Now let's see how it works. If you do this, then the similarity of A and B would be 0.09, and the similarity between A and C would be minus 0.56. So it makes much more sense now, yeah? Because A and C basically they have dramatically different tastes, but A and B seems to have a positively correlated taste, right? this is how you compute similarity to select your neighborhood. Any questions so far? Because
I know one is the movies that are rated by A and B, but why is it 5?
it's the number of movies that are rated either by A or B.
Oh, should it be 6?
A and B, right? So HP1, HP2, HP3, and TW and SW1 is 5 movies.
HP1 is not included in 5.
HP1 is rated by both A and B, right? So it should be included. It's all the movies that are rated either by A or B. So as long as it's rated by either of them, so this is, let me have it. So this is IOU, right? IOU is intersection over union. Let's say that you have, let's say that SA is all the movie rated by user A. SB is all the movies that are rated by user B. Then intersection over union means that the numerator has a intersection between SA and SB, and the denominator has the union of SA and SB. Right? Right. So this is, the numerator has only one movie, which is HP1, right? And the denominator has everything.
Oh, I see. My bad. I see why.
Cool.
I was counting HP1 twice.
Oh, I see. Cool. Yeah, union, right? It's a set. A set needs to be unique elements. Okay. So any more questions? Cool. So this is how do you compute similarity matrix. So let's have a summary of all these different methods of computing similarity matrix. Let's say that Rx is the vector that represents the user's ratings. For example, this row is Rx, right? So Jaccard similarity. The problem with Jaccard similarity is that it kind of ignores the value of the rating. Ignores the value of rating is not a good idea. Cosine similarity. The problem with cosine similarity is that it treats missing ratings as negative, right? Because and a lot of, in a sparse matrix, a lot of the entries are 0. So a lot of them are going to be interpreted as negative. So it's not a good idea either. So what we basically did in the last method is we basically computed the Pearson correlation coefficient, right? Because let's say that they ask, because we subtract the means first. So this Rx is basically the mean of the rating from X, right? So Rxs is a specific entry. So basically we subtract the mean first, and then we compute the cosine similarity. So basically we're computing the cosine similarity. Okay, cool. So we have 3 types of similarity computation matrix, right? And the last one will be the best because it subtracts the means first. Therefore, all the missing entries will be correctly interpreted as neutral. Okay. But how about rating prediction? Because we have 3 steps, right? We first we first look for 2 steps. The first step is to look for neighbors, right? And then you're going to predict the ratings by aggregating the ratings from your neighbors. So how about how do you predict the ratings? Right? The way you predict the ratings, for example, the first step would be let's say that Rx is the vector of user X's rating, right? And let's say that N is the neighbor of X, right? The set of K users that are most similar to user X, right? And because we're trying to predict item user X's rating on item I, right? So we would like to select the K users that has rated item I, right? And after we do this, we can then make our prediction. We can predict user X's rating on item I as the average of all the ratings that his or her neighbors predicted, right? So this is 1 over K because we have K neighbors, and this is the sum of K terms basically, and each of these terms is Y R Y I. Y indexes your neighbor. So this is just to look at what's your neighbor's rating, how your neighbor rated item I, and take the average. Right? And of course, you can also take the weighted average. Right? You're gonna put more weight on the neighbor who is more similar to user X. Right? So this is just to use the weighted average to make the prediction. In our example here, we simply basically just take the average, right, of these 2 users. So we're taking option 1, right? Okay. Any questions so far? This method is often referred to as user-user collaborative filtering because it can exploit the similarity between users and users, right? And then you make the prediction. You can kind of imagine that it would be certainly another type of method that's called item-item collaborative filtering, which is doing just the opposite. The method to go is, first of all, it's going to exploit the similarity between items and items. For example, let's say that we're trying to predict user X's rating on item I. Then for item I, first of all, we're going to find other similar items. We're going to find items that are similar to item I. So basically, we're going to estimate the ratings and then we're going to estimate the rating for item I based on the ratings for the similar items by the same user, right? So we can, for the similarity, to compute the similarity between between items, we can actually use a similar procedure, right? A similar procedure as we compute the similarity between users. Previously we are operating on rows, right? But to compute the similarity between items, you can operate on columns. So that's it. Everything can still stay the same, right? Yes, you can use the same similarity matrix, and also we can use similar prediction functions, right? You can take the average, right, to predict the final ratings. So basically, we're gonna use the weighted average of the same user. Let's say that we're predicting user X's. So we're gonna use the weighted average of the same user's rating on similar items. This is the overview of the idea. Next, we're going to have a very concrete example. Let's say that we have this rating matrix. We have 6 movies, and we have 12 users. And whichever is yellow, that means the ratings is observed, and the white ones means they are unknown ratings. Now, let's say that we're trying to predict this entry. So we're trying to see how user 5 think of movie 1. Right? So this is an unobserved rating, unknown rating, and let's say we want to predict it. So how are we going to do it? If we use item-item collaborative filtering, right? And we set n to 2, the cardinality of n to 2. That means we set the neighborhood size to 2. We're going to choose 2 nearest neighbors and of items and predict the rating. So first of all, we're going to compute the similarity between each items. Basically, we're going to compute the similarity between each items and item 1. Right? You can see that the similarity between item 1 and item 1 is 1. Right? That's straightforward, and you can use our previously discussed Pearson correlation or cosine similarity, right, to compute the similarity between item 2 and item 1, similarity between item 3 and item 1, and all the way to similarity between item 6 and item 1. And then you're going to pick the 2 most similar items. So which are the 2 most similar items? These would be these 2, right? So item 3 and item 6, right? And then what you're going to do? You're going to use this similarity score as the weight of the average, as the weight, right? And then you're going to compute the weighted average. Right? You can see that this user 5 rated movie 3 as 2, right? And it rated movie 6 as 3. Then we're going to predict the rating for item 1 as the weighted average of 2 and 3. And the weight will be exactly our similarity score. Right? So ultimately, we're going to predict the rating as 0.41 times 2, right? And 0.59 times 3, right? And of course divided by the sum of weights. And we're going to predict it as 0.6. Right? So this is how we do item-to-item collaborative filtering. Okay. Any questions so far? Cool. So in practice, so which one would be better, right? Item-item collaborative filtering or user-user collaborative filtering. In e-commerce, it has been observed that item-item collaborative filtering is often working better than user-user variant. And the reason is the items are usually simpler, right? It's kind of simpler and more stable. Right? And if you base your similarity computation based on using items, then your method will be more generalizable, more stable, right? And on the other hand, user can have multiple interests, and the taste can also change over time. Therefore, if you use user-user collaborative filtering, the method can be less stable. But it's actually the opposite for news recommendation. For news recommendation, item kind of change a lot, but the user's interest on news type, it actually is relatively stable. So this is the other type of problems that user collaborative filtering may be better than item-item recommender system. So let's take a look at the pros and cons of collaborative filtering. The one advantage of collaborative filtering is it works for any kind of items, right? Because we don't need to extract the features anymore. As long as you have this utility matrix, it's going to work. And it's actually usually it works better than content-based methods. But the disadvantage is that it usually runs into user co-star and item co-star problem. For example, you usually need enough users in the system to find a match. Imagine you're using user recommender system, then you need to find enough number of neighboring users, right, to compute the predicted ratings. So item quotas as well. You need to, if a new item that has not been rated, then it's actually impossible for collaborative filtering methods to recommend this item to any users. It's going to be completely ignored. And sparsity problem, right? Because now we are relying on the user item rating matrix. Right? So if the rating matrix is sparse, then this method would have a very hard time producing any meaningful results. This is another disadvantage. The last one will be popularity bias. So this is the same as similar to the sparsity problem, because we rely heavily on the rating matrix. Right? So if some items they're heavily rated, a lot of people have watched Big Bang Theory or Star Wars, Star Trek, then your recommender system will bias towards recommend these items to the users. Right? So this is called popularity bias, because you rely heavily on the rating matrix. Okay. Of course, one solution would be to combine them two, right? So to add content-based methods to collaborative filtering methods. So whenever you do not have enough rating, where the matrix is sparser, and you can automatically rely on the content part of the features, and whenever you have more ratings, you have a denser sub-matrix in the utility matrix, the method will automatically rely more on the interaction, right, between users and items. Ideally, we can do this with a hybrid approach, which we're going to talk about maybe later in the next lecture. Okay. And another thing that might help is to use demographics to handle the new user problem. So before a user joins a system, for example, before a user joins Netflix is going to ask the user what kind of genre of movies that you're interested in, right? And what age group you're in, what gender you are, and these will serve as some basic demographics to get the recommender system started, and this can be very helpful. And this is also why you see whenever you join a new app, this app will pop up some kind of forms that you to choose what kind of genres of content that you're more interested in. So this is to jumpstart their recommender system for you. Okay. Any questions so far? Okay, let's take a 10-minute break, and we're gonna resume at 11:56. Okay. Okay, let's get started. Back to the lecture. Present. Okay. So this is where we were in the first half of the lecture. So we say that we can use some hybrid methods to get the best of both worlds, right? And this will be the topic for hopefully for the next lecture next week. And so far we have talked about two key problems of recommender system. Right? The first one is to collect ratings. The second one is to how do you make predictions. The last one. So now we're gonna go into the last one, which is to evaluate a recommender system. Basically, what kind of data set can be used and what kind of evaluation metrics can be used. So usually, like any other machine learning problems, we're going to have a test set and we're going to have a training set, right? And of course, we can further split the training set into a smaller training set and a validation set. So recommender system is no different. Only the data that you're splitting is kind of more complicated. So basically, you're gonna, let's say that you have all these users and all these items or movies. You're gonna have a rating matrix, and you're gonna carve out one part, one sub-matrix as your test data set, and use all the others, right? Use all the others as your training set. And there are different ways of doing this. One way is that instead of doing this, you can, for each user, you can select 20% of his or her ratings as test set and use all the others as training set. Right? This is another way of doing this. Another way of doing this is, if, for example, if you want to measure how well your system will be when the rating is extremely sparse, then one way to do this is you can select k of his or her ratings and put it in a training set and put the others as the test set. So the reason for doing this is that you can set k to be extremely small, because if you set k to be extremely small, and the ratings will be extremely sparse as well. But in here you set it to 20%. But some users, they actually have a large numbers of ratings, right? So even 20% is actually a lot of ratings. Therefore, what you have in the training set, what you have or what you don't have in the training set is still very, very, very dense. So if you want to evaluate how performance will change when the training ratings are very sparse, you can choose for the second one. So what kind of evaluation metrics and typical data sets we're going to use? Two most classic data set people use in recommender systems, they are movie lens data set and Netflix data set. So in movie lens data set, you have 100K to 10M ratings. So because movie lens, they actually have different versions, right? So you have movie lens 100K, a movie lens 1M, and movie lens 10M. So we have different versions of movie lens dataset. This is the first dataset that's very popular. The second one is Netflix. Netflix is a dataset that has 100 million ratings. It's like millions of users and hundreds, I think it's tens of thousands of movies in Netflix. Right? So basically, these historic user ratings will constitute the ground truth, and of course part of them will be used as a training and the other will be used as testing. In terms of evaluation metrics, you can use, if you are trying to do rating prediction, so it just predict the rating from a specific user to a specific item, then if you're doing this task, then you can use mean absolute error, MAE, to compute the deviation between your prediction and the ground truth. Right? So basically, you're just computing the L1 loss between the prediction and the ground truth. right? So this is the L1 loss, right? This and this is MIE, and the other one you can use is root mean square error. Root mean square error is similar to MIE, but we're gonna place more emphasis on large deviation. So this is RMSE. If you look under this square root, you're gonna see that we're gonna have 1 over n. So n is the number of entries you will predict, right? For each entry means you have one user item pair. You're going to sum over n terms, and in each of these terms, you're going to have your prediction and the ground truth, and you're going to take the difference and take the square, right? So this is very similar to the L2 loss, because when your deviation is relatively large, your error will go dramatically up. So the model will focus more on larger deviation. So we have two evaluation metrics, MAE and RMSE. So let's take a look at a more concrete example. So in here, let's say that you have 10 item user pair. So in here, you have the user ID in this column, you have the movie ID in this column, and you have this ground truth rating. So for example, in here, if you look at the last row, user 4 rated movie 112 as 5. And this column is prediction. So our model predicts that this user will rate this movie as 4.8. Right? So if you look at this, compare this prediction and the ground truth, you're going to get that the L1 loss between them is 0.2, and the square loss of them would be the square loss, right? This is needed when you are trying to compute IMSE. The square loss would be 0.04, just basically the square of this one. And then if you sum all of them, if you sum all the columns, you're going to get 4.6, right? And then if you take the average, you basically divide this by 10. After you divide this by 10, you're going to get your MAE. So the MAE is 0.46, right? And then if you look at this one, this is your square loss, right? This is your square loss, sum of the square loss. And then if you divide it by 10 and take the square root, right? If you divide it by 10, it's going to be 0.56, and then you take the square root, it's going to be 0.75. Okay. So this is how you compute MAE and RMSE. Any questions so far? Okay. So this is rating prediction, right? It's just to predict the rating from a specific user to a specific movie. But sometimes it will be, it's actually more important to get the recommendation right instead of predict the rating exactly. So that is why we have another evaluation setting, what we call top-end recommendation. So what's top-end recommendation? In the top-end recommendation, we'll try to provide a length n recommendation list for each user, and then we're going to examine the hit items of this recommendation list. For example, let's say that we have a user, and then our recommender system will provide a rank list of 5 items. You recommend 5 items to the user, and then among these 5 items, we're going to see that this user actually, in the ground truth, right, the user have watched 3 of them. Then in this case, the results are not that bad. Right? So you recommend 5 items ranked in this order, and the user likes 3 of them. This is actually a very good result. And how do you quantify it? To quantify it, I hope you still remember the confusion matrix. So in the confusion matrix, we have the prediction and we have the reality, right? So we're going to have 4 entries, 2 by 2. We need to compute the true positive. So true positive is the number of items that are recommended by the recommender system that are actually accepted by the user. So these are the items that you recommended, and it's actually correct. Right? So this is true positive. And with the false positive is the number of items that the system predicted, but it's actually wrong. So this is false positive. And you have the false negative. False negative is items that are not recommended by our system, but these are actually items that the users like. Right? So if you look at this table 2 by 2, the first row is actually if you add these two up, then this will be the number of all the recommended items. Right? If you look at the first column and add them up, these are all the items that the user has liked. Right? These are good items. Now let's look at an example here. Our old example says that the recommender system recommend 5 items ranked like this, and among these 5 items, 3 of them is liked by the user. Right? The user feel that these 3 items are good, and they bought it. Right? But besides these 3 items, there are actually 4 other items that are not recommended by the recommender system, but the user actually bought it. So we have 4 items in here. Now let's compute the true positive. The true positive is the number of items that are recommended and actually right. So the true positive will be these 3 items, right? So this is 3. How about false positive? False positive is the number of items that are recommended, but it turns out to be wrong. So these will be 2, right? Because item 1 and item 5, they are recommended, but they are not accepted by the user. So false positive, number of false positives will be 2. How about false negative? False negative means that the items that are not recommended, but it's actually bought by the user. We have 4 false negative in here, right? Because these are the items that are never recommended by the recommender system, but still the users bought them. So in here, you can compute true positive, false positive, and false negative. And what are you going to use it for? You're going to use it to compute the precision and recall. So to compute the precision, you will have the true positive over the true positive plus false positive. Right? So the true positive, basically, they are good movies recommended, and TP plus FP is basically all the recommendations. So precision means that of all the movie that you recommended, what's the portion of it that are good movies? Right? So this is precision. And in this case, in our example, the number of all the recommendations, because we recommend 5 movies, right? Therefore, the denominator will be 5, and among these 5 movies, 3 of them are accepted by the user. Right? Therefore, the numerator would be 3, and the precision would be 3 by 5. Right? So this is the precision. And then, using these numbers, you can also compute the recall. So what's recall? Recall is a measure of completeness. It determines the fraction of items, fraction of relevant items that are retrieved out of all relevant items. So basically, if you look at this one, the numerator still is the same. The numerator is the number of good movies recommended. So it's the correct movies that are recommended. It's still 3, right? But the denominator is all the good movies. So these are all the movies that are watched or liked by the user. The denominator in this case will be 3 plus 4. Right? This is all the number of all the movies that are watched by the user. Therefore, the recall here will be 3 over 7. Right? So recall kind of measures how complete your recommendation list is, and precision measures how basically how exact or how correct it is your recommendation is. Okay. So any questions so far? So precision and recall, the numerator is the same, but the denominator is different. Okay. So typically, there's a trade-off between precision and recall, right? You can imagine that if a recommender system recommends a lot of items, then the more you recommend, the higher the recall you're going to get. But since you are recommending more items, your denominator in the precision gets really, really large, right? Then in this case, your precision kind of drops dramatically. So there's a trade-off between precision and recall. Okay? And to really kind of measure precision and recall in a single number, people sometimes use F1 score. So F1 score is just the harmonic mean of precision and recall. Basically 1 over the sum of 1 over precision plus 1 over recall. So this is basically this one. Okay, the kind of summarize precision and recall. And the optimal value is 1, of course. Optimal value happens when precision equals recall equals 1. Right? This F1 score. Another thing that's worth discussing is rank metrics. If you, let's say that for a user, and this user actually watched 2 movies or bought 2 items, the user bought these 2 items, and let's say that we have 2 recommender systems. Recommender system 1 recommended this rank list. Recommender system 2 recommended this rank list. If you compare these 2, you're going to see that this recommender system kind of does better, right? Because it ranked the correct item higher in the list. Therefore, we intuitively we would like this because relevant items are more useful when they appear earlier in the list. Because some users, they may not even read beyond the second item. So if you put it in the second recommended item, user may not even notice it. Then it's kind of a waste. Therefore, we would like to we would like a recommender system to be able to recommend the correct item as early as possible, as early in the list as possible. Right? So how do we do this? Right? How do we measure this kind of preferences using a good rank matrix? We do this using NDCG. So it's short for normalized discounted cumulative gain. So if you, NDCG is actually DCG over IDCG. So let's talk about DCG first. So DCG is discounted cumulative gain. So what's DCG? DCG basically is computed as the sum of p terms, and in each of these terms, we're going to have the relevance in the position. So relevance I means whether there is a hit in position I. Okay, it's a binary value. So think of it as a binary value. If it's a hit, then relevance I would be 1, otherwise it would be 0. Right? And the denominator will be log of I plus 1. Right? So I, because this is where it's really related to the position, because when I is larger, then the log of I plus 1 is larger, right? Then the denominator is larger. That means you're putting less weight. You're putting less weight on the position I if I is larger. So if you compute, let's say that if you compute the DCG in this rank list, how do you compute this? First of all, you're going to compute the I equals to 1. So when I equals to 1, if you look at this rank list, it's not a hit, right? It's not a hit. Therefore, the numerator is 0. If the numerator is 0, then the whole thing will be 0. Now let's go to the second position, I equals to 2. If you look at I equals to 2, it's actually a hit. Therefore, the relevance of 2, relevance of I where I equals to 2 is 1, right? And this log 2 of I plus 1 will be log 2 of 3. Right? And you compute this value for these 5 rows, and you add them up, and this is your DCG. So this is your DCG. And this DCG is actually an unbounded number, right? It's not like an accuracy where you know that it's between 0 and 1. It's actually an unbounded number. So how large is large enough? Right? You don't know that. So this is why you need to normalize it such that you can be sure that this matrix is between 0 and 1. And this is why you need IDCG. IDCG is ideal discounted cumulative gain. This is like ideal DCG. And in an ideal DCG, you pretend that your recommender system perform perfectly. Basically, you rank all the relevant items at the top, and you put all the irrelevant items at the end, and you compute the DCG. Right? So this is IDCG. Okay, and you compute DCG, and you compute IDCG, and then you take the value of DCG divided by DCG, and this is your normalized DCG. And the normalized DCG can kind of measure how good your ranked list is. This is a rank matrix. This is probably the most commonly used rank matrix to measure how good your ranked list is, and it's very commonly used. Let's have an example to see how it's computed. Okay, let's say that we have a recommender system, and the recommender system does this one. So the recommender system recommends 5 items, and 3 of them are correct. Right? And this is what an ideal recommender system would do. An ideal recommender system would put the 3 relevant items at the top of that rank list. Okay? We're going to use this table to compute DCG, and we're going to use this table to compute IDCG, and we're going to divide them to get our NDCG. Right? So to compute DCG, we look at this table, and you can see that only three items are relevant, right? The first one is in the second position. So if it's in second position, it's a 1 over log of 1 plus 2, right? Because in the second position, the second item that's relevant is in the third position. Therefore, it's 1 over log of 1 plus 3, because it's in the third position. And you're gonna add another term, which is 1 over log of 1 plus 4, right? It's the last item here. And then you're going to sum them up. This is your DCG. Your DCG will be 1.56. And to compute IDCG, you do this similarly. The first item, if the first item is correct, then it's 1 over log of 1 plus 1, right? Plus 1 over log of 1 plus 2, because this is the second item, and plus 1 over log of 1 plus 3. And the ideal DCG would be 2.13. And then you can compute the normalized DCG. The normalized DCG would be this one divided by this one. So it's going to be 0.773. This is a very, very high number. This is a very, very high NDCG. If you have a recommender system can do this, that would be very, very, very powerful. Can make a lot of money for Netflix or Amazon. So this is NDCG. Before I move on, is there any questions? Okay. Another matrix that can measure how good your ranked list is will be average precision, or sometimes we call it mean average precision. If we compute the average score for all the users. So let's talk about what is average precision. So by definition, average precision is the average of the precision, and it's the average of precision at up to different position. Right? And then similar to NDCG, we only care about the precision that we have a hit. So basically, we're in here. For example, if this is the rank list produced by the recommender system, to compute the average position for this list, we're gonna look at the precision up to here, the position up to here, and the precision up to here, and then we're gonna take the average. So let's look at it one by one. Okay. if you compute the precision up to position 2, then you're going to see that up to position 2, you have recommended 2 items, and one of them is correct, right? Therefore, the precision is 1/2, right? Precision is 1/2. So one of them is here. And then if you look at the precision up to here, and up to here, you recommended 3 items, and 2 of them is correct. Therefore, your precision will be 2/3. 2/3 is here. And then you look at this position. If you recommend item up to this position, you recommend 4 items, right? And then 3 of them is correct. Therefore, the precision is 3/4. Right? 3/4. So you're going to sum these 3 positions up and take the average. So this is your average precision. Average precision is 0.639. And you can do the same for this recommended list. And you're going to find that it's actually higher than 0.7. So why is it higher? Because you have the relevant item at the top. So this is like what we discussed. It's actually very important to place the correct item at the top, because people distribute their attentions not uniformly across the list. People may pay much more attention at the items at the top of the ranked list, right? So if you can place the correct items at the top, then it will be very beneficial for the recommender system. So this is intuitive, and that means average precision is actually a good matrix. It's a good rank matrix. So this is the average precision for one user, right? And if you average over the average precision for all the users, you get MAP, so mean average precision. Okay. Any questions so far? Cool. So this is the first part of the lecture where we talk about the first 2 approaches of recommender system. We talk about content-based methods and collaborative filtering-based methods. And we also cover how do you evaluate recommender systems. Okay. And next, we're going to talk about the third type of approach. Let me see. Which is latent factor models. So, as I mentioned, we have 3 approaches to recommender system, right? 3 typical approaches: content-based, collaborative filtering-based, and latent factor-based. And interestingly, sometimes people will call latent factor models as model-based collaborative filtering. So there is this kind of naming issues in different papers. Okay. So what is latent factor models? Before we talk about this, let's kind of lay some background on why latent factor models become very popular. It becomes very popular because it kind of performed very well in the Netflix prize. What's Netflix prize? You know, in 2009, Netflix decided that it's going to put up a competition, and the competition is that if Netflix has an in-house recommender system, right? It has in-house recommender system that can achieve an RMSE of around 0.95 something, and Netflix says that I'm going to hold a competition, and if any one team that can develop a model that can reach a RMSE that is 10% lower than my in-house system, then I'm going to provide a 1 million prize for this team. So this kind of draw the attention for over 2,700 teams around the world to join the competition. And so what's the setting that's laid down by Netflix. So in that year, 2009, Netflix provided 100 million ratings of data. So in these 100 million ratings, they actually come from 480,000 users, and these users provide ratings on over 10,000 movies. Okay, so this is the number of users and number of items, and this is actually 6 years of data, 2000 to 2005. Okay, and this is a training data. In terms of test data, Netflix used the last few ratings of each user. So this is about 2.8 million ratings as test data, and the evaluation metrics is IMSE. Right? So basically, you're gonna compute the IMSE of between your prediction and the ground truth, and the lower the better, right? And in Netflix's in-house system, IMSE is 0.9514. If you can lower this by at least 10%, then it's gonna give you a 1 million price. Okay. And in this competition, latent factor models play a central role, and it basically provide a very large potential, bringing down the IMSE by a large amount. Okay, let's go back to our utility function. So basically, in Netflix data, you're gonna have 17,700 movies, right? And you're gonna have over 400,000 users. So this is a very, very large rating matrix. And you're gonna carve out a part of them as your test data, and all the others will be used as a training data. And you're going to use IMSE as your evaluation matrix. So IMSE basically compute the average error of your prediction. Right? So this is your predicted rating from user X to item I, and this is the ground truth rating of user X on item I. Right? And take the difference and take the square, take the average and take the root. So this is IMSE. And if you can achieve a very low error, then you get $1 million. Now the winner of recommender system is the Team Belcourt. Okay? So Team Belcourt is the winner of the Netflix challenge. And interestingly, there is another team. So we all know that in machine learning we have a training set, we have validation set, we have test set, right? So usually this kind of competition, they allow the teams to submit their results for a validation set, and the result for the validation set will be published after each day. So there is actually another team which beat Belcourt in terms of validation set by a small amount, but the true prize is decided on the test set. So ultimately, Belcourt actually achieved a better test set result, actually slightly better than, and Belcourt win the competition. So what does it mean? It means that overfitting can also occur on the validation set, right? You need a very, very robust model to prevent you from overfitting both on the validation set and the test set, and the performance can be very different. Right? So going back, this Belcourt team, they use a multi-scale modeling of the data. So basically, their model has 3 parts. Right? You can, roughly speaking, they have a global component of the model to model the overall deviation of users and items, and they have a factorization part of the model. So this is a latent factor model that adjusts the regional effect, and they have a collaborative filtering part of the model that extract the local patterns. So this is basically a 3-layer model, and we already talked about the collaborative filtering part, right? So this extract local pattern from local neighborhood. So next in this in this lecture, we're going to talk about the first two parts. We're going to talk about the global model and the regional model, okay, in detail. So the idea of a global model is actually extremely simple. So let's say that you look at the training set and you find that the mean movie ratings in the whole training set is actually 0.7. So on average, people rated 0.7 stars. And let's say that you're gonna try to predict how Joe will rate the movie The Sixth Sense. Okay. Then after getting the average rating of 0.7, you're going to look at the average rating for the movie The Sixth Sense, and you find that the movie Sixth Sense, the average rating for this movie is actually 0.5 above the average. So basically, it's a relatively good movie compared to other movie. So it's actually 0.5 stars above the average. And then you're going to look at Joe's rating. Joe's other ratings on other movies, on other movies that is not The Sixth Sense. Okay, then you're going to find that Joe is kind of critical. Joe's rating is actually 0.2 stars below the average. Right. Then, based on these statistics, you're going to predict that Joe will rate The Sixth Sense as 3.7 plus 0.5 minus 0.2. So this is 4. So this is what your global model would say. Basically, it's going to predict the rating as the global mean plus the item bias plus the user bias, right? And the ultimate result would be 4. This is what the global model will predict. And they actually provide a fairly good starting point of the model. Right? And then, of course, you can combine this global model with the local neighborhood model, or our collaborative filtering model, right? And your collaborative filtering model may find that, for example, Joe, there's a related movie called Science, and you may find that Joe actually didn't like the related movie Science. Then you're going to further lower your estimate of Joe's rating by 0.2 stars, and you're finally going to predict that Joe's will rate The Sixth Sense as 3.8 stars. So this is basically how the global model would work. Okay. Any questions so far? At this point, it's more like some very simple heuristic that can achieve good results. Okay. And let's take a look at kind of refresh our memory on collaborative filtering. So earlier we talked about the collaborative filtering methods, right? And in collaborative filtering, the key is to define a similarity, right? Define a similarity between different items, right? If we talk about the item collaborative filtering variant, the key is to compute a similarity between each pair of items, and then you're going to predict the items, the ratings from user X to this item as a weighted average of all related items, right? So this Rij. J is one of the items that are similar to item 1 to item I, right? And Sij is the similarity between item I and item J. So this kind of decides the weight of the rating from item J. So you're going to predict it as a weighted average of similar items. Right? So this is item collaborative filtering. Now, one question is, how do you combine our global model with a collaborative filtering model? Right? And we do this using by directly adding and subtracting the bias term. So this BXI is what we have been doing in the global model, and this is the baseline estimator for RXI. RXI is the rating from user X to item I. And this BXI, for example, this would be our estimate of the global bias plus the user bias plus the item bias. Right? And because you added a bias term here, and up here you need to subtract the bias term back. Right? So this is to subtract the bias term back. Only in this time you're subtracting the bias term for item J. Yeah. So basically for each user and item, you're gonna have to compute a specific bias term, and the bias term is the sum of preterms. Okay. Now this is how you naively combine collaborative filtering based methods and the global model. Right. So you can compute the similarity using our previous methods, but and then you can predict the ratings using a combination of our global model and our collaborative filtering model. One problem with this method is that the key of collaborative filtering method is the computation of the similarity between items, and this computation seems quite arbitrary. You kind of have an ad hoc rule of computing the similarity. For example, you say that you need to use Pearson correlation or cosine similarity. Is kind of not very principled method. And another thing is this pairwise similarity kind of neglects the interdependence among users, and they only take a weighted average. Right? Take the weighted average can be also restricting. Kind of how about a nonlinear combination of different methods? So the solution to make it more flexible is, instead of computing the similarity between each pair of items directly using some kind of fixed functions like cosine similarity, we're gonna learn this similarity from data. So we're gonna replace Sij with Wij, and we're gonna learn this Wij directly from data. So how do we do this? We're going to replace. So you can see that this is actually a weighted average of ratings from similar items, right? So we're going to replace this weighted average, the weights of this weighted average, with Wij. So this is the original one. We're going to replace Sij over the normalizing constant with Wij, right? And then we're gonna learn this Wij directly from data. Okay? And here, Nix is very similar, right? As our old equation. Nij is the neighbor. Is the neighborhood. Basically, it's the set of movies that are also rated by user X, and that is similar to movie I. So this basically it's the neighborhood of movie I in all the movies that are rated by user X. Okay, and Wij is we call it the interpolation weight. So it's going to be some real number, right? And you can think of it as a learnable version of the similarity between I and J. And it's actually more flexible. One reason is that it's directly learnable from the data. The other is because we do not have this constraint of if you sum them up, it has to be 1. So it's actually more flexible. So we can see that this Wij, it models the interaction between pairs of movies, right? So it does not depend on user X here. And if you treat this equation as the predictive ratings, then the rest of the story kind of know what to do. Right? You just have a L2 loss between your prediction and the ground truth. Right? Remember, our error matrix, our evaluation matrix would be RMSE, right? Well, RMSE is a root mean square error. A root mean and square error. The square error of what? The square error between the prediction and the ground truth. Right? And if you look at this root mean square error, you can see that it's actually equivalent, because it's a monotonic function. It's actually equivalent of the sum of square error. Right? Whenever the sum of square error is larger, MSE would also be larger. Right? Therefore, you can actually use this SSE as your objective function to train your model. Right? Basically, the only learning part here would be to find Wij that can minimize the SSE on the training data. Okay? That way you can automatically learn the similarity between each pair of items. Right? And basically we're going to have this objective function. In this objective function, we're going to sum over all the user item pair, user X, item I, right? And this whole thing is the predicted rating, right? It's exactly the same as what we laid down before. And this is a true rating. And we're going to take that difference and take the square and sum them up, right? Sum over all the item and user pair. Right? So this is going to be our objective function. And if you look at this objective function, only Wij is learnable. Now, all the others, they can be computed right from the data. Right? And this is the ground truth that's provided by the data. Right? And this one is also provided by the data. So everything is actually fixed except for the W, which you need to learn. And you learn W by using, of course, gradient descent, right? To give you some kind of a refresher. So basically, let's say that you would like to find X that can minimize f of X, right? Basically, you're going to first of all compute the gradient. You're going to start somewhere. We're going to start somewhere here, and then you're going to compute the gradient along this direction, right? And then you're going to move to the opposite direction of this gradient. You're going to move here, and then you're going to see that if you move in the opposite direction of the gradient, you're going to reach a point where you have a lower value of f of x, right? So basically, you're going to do gradient descent, right? And in this case, we're going to take the gradient with respect to Wij, right? We're going to take the gradient with respect to Wij. Basically, we're going to use a train rule, right? We're going to first take the gradient of this objective function with respect to this whole thing inside the square, and then we're going to take the derivative of this whole thing inside the square with respect to Ij. So this is what we have right now. We're not going to talk about how to derive this in detail. I'm going to put it as an exercise, but you can kind of see that this is the update route, right, for Wij, and you're going to assume that all the other entry of Wij is fixed, right? And then you can update this specific entry of Wij. Okay. And in modern computing software, like PyTorch, you can kind of directly define the objective function, and it's going to compute the gradient for you automatically. So that's kind of convenient too. And you don't even need to derive the gradient, not like in the old days that we have to manually derive all these gradients and write it in the code. Okay. So after you learn W, then everything would be very, very straightforward, right? You can just predict the rating that user X gives item I as using this exact equation that we laid down before, right? Just have a bias term, the global bias term, plus the sum of a weighted average of items that are similar to item I. Right? So basically, the weights derives based on their role in the data, and we're not using any arbitrary similarity measure like cosine similarity or Pearson correlation to compute W. So it's kind of 100% data driven, and therefore it's more flexible and usually performs better. And it also explicitly accounts for the interrelations among the neighboring users as well. Okay. So any question so far? The basic idea is to make one of the numbers learnable, and we learn this through data to improve the performance. Any question? Okay. So if you look at the performance of different methods, you can see that the global average, if you simply predict the global average of the whole training set, you're going to get a INFC of 1.12, right? And if you for each user, if you simply predict the user average, of course plus the global average, then you're going to get 1.06. Right? If you further incorporate the item average, so this is going to be our global model already, right? You're gonna, in the global model, we have the global bias, the user bias, and the item bias, right? If you use these three, then you're going to improve the performance to 1.05. And although it's still kind of relatively far away from Netflix in-house model, right? This is Netflix in-house model. And then if you use basic collaborative filtering, like what we have talked about in the previous, the first half of the lecture, we're already doing a little bit better than the Netflix one in-house model. And if you use collaborative filtering plus the biases, right, plus the global bias, item bias, user bias, and the learnable weight, we're gonna get 0.91. This is actually a lot better than the in-house model already. Okay. And the grand prize, in order to have to win $1 million, you need to go to as low as 0.85, which is actually very difficult. So this is where the latent factor model comes in. With the latent factor model, you can have potential to further bring down the IMSC and bring you closer to the grand prize. So next we're going to talk about this latent factor model. It's kind of, you can think of it as extracting regional correlation between users and between users and items. So latent factor model, by definition, is trying to embed each items or movies in a latent space. For example, if you have a latent factor model, we're going to try to embed each movie in the, for example, in the 2D space, where the horizontal axis kind of shows you if it's more to the right, then it's more like action movie. If it's more to the left, then it's less like action movie. And in the vertical axis, if it's further up, then it's more serious movie, and it's in the bottom, it's a more funny movie. So you can kind of embed different movie in this two-dimensional space. So this is, you can think of it as a latent space. And you put the movies in the latent space, and then you also can put the users in the same latent space. And then for a specific user, you're going to recommend to this user the movies that are close to him, right, in this latent space. For example, for this user, probably we're going to recommend the movie Dumb and Dumber to this user. But for this girl, probably we're going to recommend The Princess Diaries for this girl. Okay, so it's close in the latent space. So what's the good way? What's a good way of doing this? The good way of doing this is we can, for example, factorize the large rating matrix into two matrices. We factorize it into a a tall and thin matrix, the product of a tall and thin matrix, and a fat and short matrix. Right? And if you look at this, each row of this rating matrix is one user, right? And each column of this matrix is an item. So if you look at this one, this is actually the same, right? Each row of this matrix P represents one user, and each column, we have 3 columns here. That means we have 3 latent vectors, right? We have 3 latent vectors. We use 3 latent vectors to represent each user. And similarly in here, each column in this matrix Q transpose represents 1 item, right? And each row, we have 3 rows. That means we're going to have 3 vectors to describe each item. Right? And if you multiply these two, it's gonna approximately recover the rating matrix. Right? So the key here is to find two low rank matrix, right, that can approximate this full rating matrix. Okay. And one way to do this is to use SVD. Right? We already know SVD in our previous lectures. SVD try to factorize a matrix into 3 matrices. Factors I into U times sigma V transpose. So and such that this sigma is gonna contain the singular value for this matrix. The sigma is a diagonal matrix, right? And U and V, they are orthogonal matrices. And then if you, let's say that you know how to perform a singular value decomposition, SVD, then you can use you can use the product of U and sigma and use it as P, right? And then you can use V transpose as Q transpose. So that is it, right? You do a SVD, and you use the first 2 matrices as P and use the last one as Q. And then you can do whatever you want to predict the matrix. So kind of more about SVD, just to refresh your memory. So SVD tries to decompose a matrix into the product of 3 matrices, U, sigma, and V. Right? And the sigma is a diagonal matrix. And U and V are orthonormal, or someone's also called it orthogonal matrices. Right? So in our case, we're going to do SVD on the Netflix data. So this is a Netflix rating matrix, and we're going to do SVD, and then we're going to set P as U times sigma, and we're going to set Q transpose as V transpose. So A is R here. This is how we do matrix. So this is why this latent vector model, it's sometimes called matrix factorization method. Okay. And after we do this, let's say that we are trying to, after we factorize this matrix into 2 matrices. Now, in this rating matrix, we have a lot of unknown ratings, right? Let's say that we're trying to predict one of the unknown ratings here. What are we going to do? We want to predict how user 2 would rate item 5, right? To do this, we're going to look at the latent factors of user 2, and we're going to look at the latent factors of item 5. Right? So this is a 3-dimensional vector. This is a 3-dimensional vector. And we're going to take their inner product, right? And then the inner product is 0.4. Therefore, we're going to predict the rating as 0.4. Right? So inner product is just this one times this one plus 0.6 times 0.3, right? Plus 0.5 times 0.4. Right? So this is a sum of all the product terms, basically. No, any questions so far? So this is just a high-level overview of how you can do latent factor models using factorization methods, and how do you predict an unknown rating once you finish the factorization. Any question? Okay. So, like I said, in latent factor models, basically you embed, right? You embed each movies in a latent space. You look at the latent factors. You look at each column. Each column represents one item, and you can plot it in the latent space. And you can do similar things for the user, and then you're going to recommend to a user using the items that are close to the user in the latent space. Okay. What's good about SVD? So this is more good stuff, and it's more like a theoretical guarantees of SVD. So using SVD, it can actually give you the minimum reconstruction error. Right? If you remember, the SVD tried to factorize a matrix into 3 matrices, right? And if these matrices, they actually rank in the order of the magnitude of the singular value. Right? If you choose the first 2 singular value and its corresponding U and V, this SVD actually guarantee that this is actually the best choice you have in terms of minimizing the reconstruction error. Yeah. The one thing is that, again, we have talked about this before, as sum of square error and IMSE, they're actually monotonically related. Right? So the Netflix competition use IMSE as evaluation metrics, right? But SVD, it guarantees that you can get the lowest sum of square error. But since they are monotonic, that means SVD can actually guarantee that you can minimize the IMSE as well. So this is good, right? But the complication of SVD is that the sum of the sum in this SVD error term is actually over all the entries, right? But in practice, we have a lot of unknown ratings, right? And it's actually a little bit tricky how to represent these unknown ratings. In our previous example, we kind of directly set them to 0, right? You directly set them to 0, and you perform an SVD. This is actually not a good idea. So how do you do this? Well, in practice, people actually do not use SVD directly because you need to handle the missing value. In practice, people use another objective function. So the objective function still is trying to minimize the reconstruction error. Right? This is the ground truth rating. This is a predictive rating. Right? Still, they're trying to minimize this, but they only care about the entries that are known. So this is no longer all the entries, only the yellow entries, basically. Right? So we're going to try to find matrix P and Q such that the predictive ratings and the ground truth rating, they are as close as possible, right, over all the known entries. Okay. So in this case, we're going to relax one of the constraints. Remember, in SVD, we actually require P and Q to be orthogonal, right? But when we're solving this problem, we actually don't care about orthogonality anymore. So we only need a P and Q such that we can map users and items into a latent space. And this is actually the most popular model among the Netflix teams. And you're going to see why later, because it performs very well, and it's very easy to incorporate other domain knowledge into the model. So this P of X is basically the axis, the X row of the matrix P, right? And QI is the ith row in the matrix Q, right? So basically, you're going to find the whole matrix such that this reconstruction error can be minimized. Okay. before we go into more details on how to find the latent vectors, is there any questions so far? Okay, I'm going to briefly talk about how you can find the latent vectors before we run out of time. And we're going to continue in the next lecture. So basically, our goal is to find a P and Q such that these objective functions can be minimized, right? Then again, what we have, ideally we want to minimize the reconstruction error on the test data, but in practice all we have is the training data. Right? In practice all we have is the training data. Right? So the only thing we can do is to minimize the reconstruction error or the prediction error in the training data. But one thing that's very important is that we have a number of factors. This is hyperparameters to choose. Right? The larger we choose the number of factors, we call it K here. The larger K is, the smaller the training error will be. Right? So this causes an issue, which is overfitting. Right? If you choose K to be larger, then you can infinitely approach a zero training error, but ultimately you're just fitting the noise. Your model will be severely overfitting. It doesn't give you anything. So again, this is some intuition, right? I hope you still remember. If your model is too simple, let's say that you have the positive samples and negative samples. Right? If your model is underfitting, then it fails to capture the complicated patterns. If it has a good fitting, then you can see the model is very good. If the model is overfitting, that's when you have many more parameters than needed. Then the model is going to overfit. It's going to perform very poorly on the test data. Right? So in order to alleviate this overfitting, we're going to resort to our old friend, which is a L2 regularization. So besides minimizing the training error, we're going to add two regularization terms. So one of the regularization terms is on the user latent vector, right, Px. The other one would be Qi, which is the item latent vectors. Right? We're going to add these two regularization terms such that we can prevent overfitting. Right? And then the rest of it is relatively simple. Right? You just use gradient descent or stochastic gradient descent to solve for the optimal Px and Qi, right? Such that this objective function can be minimized. Okay. So I guess this is it for today's lecture.